So we can do this here. Now, this is normally the part where if you do have homework questions, because I already asked that here a minute ago, didn't have any. So if you did, we would go over one or two of the problems here. We do it together and answer the questions that you have. And I do this mainly because if you did have questions or something didn't make sense, we could go back over it. Because if you're working on it, and especially if you're sitting there spinning your wheels for more than 10 minutes and making no progress on it, move on, do some of the others. And we can go over it here in class. I don't want you spending 10, 20, 30 minutes on a problem and getting nowhere. Either email me or we can cover it at the start of class. Now, what we're covering today is parent functions. We're going over parent functions. Now, parent functions are the most basic version of each of the different types of functions that we have. Now, we have four here. We have the constant function, which parent function is f of x equals 1. So any line, just flat line that you've seen up to this point, goes or is a part of the constant functions. It's just a constant function, flat line. Linear, f of x equals x. You all have seen these. You've seen them in Algebra 1. You all have done many of these. F of x equals x plus 3. F of x equals 1/2 x minus 7. All of those are linear functions. And they all look similar to the linear function. It's just a line. It's either going up or it's going down. Absolute value is always going to make a V shape. It's our absolute value bars. So any other absolute value function, its parent's this. We just change these here. Or quadratic, our U shape, x squared. So all quadratics are parents. This is its parent function. Now the reason that we call them parent functions, because as I said, they're the most basic. All the others are we're just taking these functions and applying a transformation to it. We're applying a horizontal stretch, shrink, reflection, vertical stretch, vertical shrink, horizontal stretch, horizontal shrink. We're moving it left, right, up, down. We're flipping it. We're stretching it. We're shrinking it. We're applying some type of transformation to it. All of them will look similar to these here, to these parent functions. Not the exact same, but they look similar. That's kind of why they call them the parent function. They all come from these here. Questions on this so far? Now there are more than just 4. Because cubic, x to the third, does have a parent function. We're not going to look at it here. 1 over x is a parent function, but we're not going to look at it. So there are others. There's more of them than just these 4. But for us, these are the 4 well, really 3. Because constant function doesn't tell us a whole lot. Vertical stretch, vertical shrink doesn't do anything. Horizontal stretch and shrink doesn't do anything. Really, you can move it up or down. That's it. Because I can move it up 3, now it's 4. I can move it down 3. 1 minus 3, negative 2. I can move it up or down, that's it. There's nothing else to it. So the main ones we're going to look at are linear, absolute value, and quadratic. Now there's many different types of transformations. Well, I say many. We have up, down, we have left, right. We have vertical stretch, shrink, horizontal stretch, shrink, and reflections across the x or across the y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10. We have 10 types of transformations that we can do. That's it. Okay? Now, linear. Absolute value. Quadratic. These are the 3 main ones we're going to look at. Okay. Okay. Now what we're going to do, and we're going to list these out here. I would write these down. I'm going to give you all the general form. So when we talk about the general form, it is a form of the equation that works for every single type of linear, quadratic, and absolute value we can have. They're not all going to look like it because some of the values are going to be 1 or 0 or not show up in those spots. But these cover every type that we could have. Okay? So linear. So linear is the first one we're going to have. Now, f of x. F of x is just a way to name it. Because you all have seen f of x before, you've seen g of x, yes? It's just another way to write y. Is equal to a times x minus h plus k. Again, this is the general form. General form. We don't have to have a value for a, h, and k. A, for the most part, we will have a value for it, it'll be 1. If nothing's applied there, nothing is applying that type of transformation, it's going to be 1. We don't have to write it's doing nothing. H and k, if they don't show up, they're going to be 0. They're just not going to be there. Does that make sense? Absolute value is equal to a absolute value of x minus h plus k. Kind of looks the same, but this time we have our absolute values, yes? Quadratic. F of x is equal to a parentheses x minus h squared plus k. They all pretty much look similar. It's just one has our quadratic, the x squared, our squared term. Our absolute value has absolute value bars, and linear just has an x. Questions on these so far? Now, each of these, a, h, and k, if we have a value at a other than 1, it will apply a transformation. Either stretch, or we'll get to it, but it's really going to be our vertical stretch or shrink and reflection across the y-axis, or sorry, x-axis. H and k are going to be moving left, right, up, down. If there's no left or right movement, it's going to be 0. If there's no up, down, it's going to be 0 for that value. And yes, that kind of doesn't make a whole lot of sense at this point, but we will get there. All right? So we good with this so far? Now, we will keep coming back to this slide, this page, as we fill information in. So the role of h across all three is going to be the same. The role of k is going to be the same. The role of a, all of them are going to be the same. So in years past, I've specifically written under a, this is what it does. Under h, what it does. And it gets messy. So we're going to list them out below. And again, remembering not so much case by case, but h is going to do this. K is going to have this property. A is going to have this property. And it's about what's in that place, not so much all the specifics. So this is our next slide on the back of that first page. The transformation changes size, shape, orientation, or position of a graph. Up, down, left, right, make it bigger, smaller, stretch it out, stretch it tall. That's a transformation. A translation is a transformation that shifts the graph horizontally, up and down, left and right, vertically, up and down, horizontally, left and right, but does not change its size, shape, or orientation. All we're doing is just moving it around the graph. We're not changing anything about it. We're just moving it up, down, left, right. Everything else stays the same. Okay? Now, the one that does this is H and K. H and K move it up, down, left, right. Not together, but they do individually. With these here, H, and this is across all three. H is our horizontal translation. It moves it left or right. H moves it left or right. And that's for all three. Okay? Because again, Normally, I drew a little arrow and wrote above it left, right, left, right, left, right for all three. As I realized this morning, again, I keep forgetting that it gets a lot for each one. So let's just make it a little bit simpler. H across all three translates it left or right. There's a little bit of a stipulation with it. We'll see it here in a minute. Because if H is negative, it's going to move it to the left. If H is positive, it's going to move it to the right. K is our vertical. Translation, which means it's going to move it up or down. If K is positive, it's going to move it up. If K is negative, it's going to move it down. Questions on this so far? Now, for the most part with linear, H isn't going to do a whole lot. Because it's going to end up being that H and K, for the most part, is going to do about the same thing. There's only a few cases where it doesn't, but for the most part, H and K are going to be about the same. All right. So we're going to look at our first example, this here. Graph, g of x equals x minus 4 and its parent function. Then describe the transformation. Okay. Now, for the most part, I'm not too focused on graphing. It's not because I dislike graphing. It's just that, for the most part, at this point, we have so many tools that can graph for us. Right? Because in the last, especially in the last decade, if not more, because when I was in high school, and even when your parents are even farther backward in high school, the thing that I heard from my teachers is that you'll never have a calculator or have something that like that in your pocket every day. You've got to be able to understand how to do this. That era is gone, because our phones now are as powerful as most calculators. They are strong enough they can do this. So I don't see the whole reason for us to actually meticulously know how to graph, because, especially for us, the 84s, the graphing calculators, I still have not put out, can graph for us. In this first function that we have, this first problem we're looking at, d of x equals x minus 4. Its parent function, you all know which one it is, because we have, well, 4, but it's really one of 3. Linear, quadratic, or absolute value. It's linear, because we just have x, yes? So the parent function would be y equals x, or I will say f of x equals x. This is the parent function. So this right here, it just graphed it for us. And we, again, I will show you, we will have a day and we will work through actually how to use these. And especially once we get comfortable using these, I would say having them out and following along is going to be helpful, because especially come test time, you're going to be comfortable using them. Also, y'all are all juniors, you're going to have to take the ACT at the end of the year. These calculators are allowed on the ACT, so you can use them. Now, our new graph, the one they gave us, g of x was x minus 4, yes? What they told us? Okay. So let's see how this changes. How does it change compared to the one in blue? What happened to it? It went down. We moved the whole function down 4, yes? Okay. So this here, its parent function, we would call it linear. Describe the transformation. Down 4. And that's just looking at the graph. Okay? We feel comfortable with this so far. Awesome. Now, our general form for this here, this is a different f of x. I should have used something other than that. A times, what's this here? This is the general form that we had. Yes, we wrote it on the previous page. So A is 1. So we haven't even talked about A. The main ones we've talked about is H and K, yes? Are there parentheses around our X and G of X? Well, there are, but they're not written. So what that means is the H value here, the minus H, there is no horizontal. There's no movement left or right because there is no number to represent H. It has to be inside the parentheses. All right? So our 4 is attached to which one? The K, yes? And what did we say K does? It moves the function where? Up or down? Vertical, yes? So how much are we moving it up or down? 4, because that's the value of K, yes? And it's positive or negative? Negative. So since it's negative 4, it's moving that's it. So what do we think of that? We good? All right. So in this here, and the whole reason I want to cover this is something that is not necessarily essential, but it's helpful. Because we can look at this, x minus 4. We know it's linear because of the x. The minus 4 tells us it's moving down 4. It gives me an idea of what the graph should look like because we know parent functions going through the x-axis. Down 4, it should drop down 4. It gives us an idea of what the graph should look like so we know how it should behave. We can predict of what it's going to do. And that's it. That's the key. Because if we can do that, that's going to help us. If not, graphing calculator can help us. That makes sense? Because it's more about getting a picture than having a firm understanding being able to graph this meticulously. We ready for the next one? What is its parent function? Absolute value. This kind of gives it away, doesn't it? Because it has absolute value bars. This one, I'd almost just have to ask the parent function and not read it, because if I read it, well, this g of x is equal to the absolute value of x plus 1. Kind of says it, doesn't it? Absolute value. And the parent function is, I'm just going to call it h of x. There's no real reason, just so it's not, when we put the generic version of it with f of x, we're not getting confused. Now, h of x, g of x, z of x, q of x, all of those are just a way to name the function so we know which one we're talking about. Now, when you had, all of y'all had Miss Kendall, and if, I don't think any of y'all had me last year or in Algebra 1, and y'all dealt with absolute values, we told you the 30xs does not do absolute values. There's not a good way to do it on this here, yes? Graphing calculator will actually do absolute values. So what I can do here, I'll clear both of these out, and I can go math, remember ABS, graph. It'll graph absolute values. Now the one that it gave us, absolute value of x plus 1. How did it change? It went to the left. How far? By 1. And if we look at the graph, because the original, the parent function, when x is 0, y is 0, yes? Well, for the new one, when x is negative 1, y is now 0. We moved it 1 unit to the left. So the transformation is left 1. So we did that graphically, looking at the graph and having it tell us that, yes? Let's look at it in the general form. Now in the general form for this here, we have a times the absolute value of x minus h plus k. Is there a value for k? Well, no, there's nothing being added outside. So it's not moving up or down. There is no up or down movement. And again, we haven't talked about A, and there is no A value. There's no transformation there. So the one that we have is H, yes? Well, what is the H value? 1. Is it positive or negative? It looks positive, right? Because it's plus 1, yes? So looking at that, the plus 1 tells us it should do what? Move 1 unit to the, well, what did the graph show us? Left. Yes. And there's a reason for it. Because look at the general form. It is what? X minus H. Yes? The one that we have is what? X plus 1. What is the only way that we can change a minus into a plus? Is with another minus, yes? So realistically, what we're seeing here is not so much x plus 1, but x minus negative 1. Because we don't leave a negative negative. Because if we minus a negative, we just rewrite it as a plus, yes? Anybody getting confused yet? It makes sense, but it's a little bit to wrap our head around. We're used to negative negatives. But in this context, it's a little stretching, yes? So the big thing I say, especially with any of these here, the horizontal, left to right, inside those parentheses are absolute values. It's the opposite of what we think. So we see plus 1, which tells us that we feel like it should be right 1, but it's actually left. And if it was minus, it seems left, but it's actually to the right. So this is still left 1, because the value of H is negative 1. That's it. Yes, sir. Yes. So especially inside parentheses are absolute values, and this kind of goes across the board. It's going to be the opposite of what we think. So we talk about horizontal stretch and shrink. We haven't had it listed here yet. It doesn't apply so much with reflection. I'm going to go back to these here. There is actually a value, you don't have to write this in, of a specific value that we could say B that goes in front of X. This is where horizontal stretch or shrink comes in. And what's funny about it is, and we'll cover it, because it's not too bad again. It's just like horizontal translations, moving it left to right. When it looks like it should be a stretch, it's actually a shrink. When it looks like it should be a shrink, it's actually a stretch. It's kind of flipped. But as long as we remember that, it's not too bad to keep track of. And at this point, we're not covering it in this section, so I'm not putting it there, but there would be a value there. There can be a value in front of that X inside the parentheses. So we feel good about moving it up, down, left, right. Yes? All right. A reflection is a transformation that flips a graph over a line called the line of reflection. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So I believe y'all did this in geometry. You had a shape, and you drew a line and then counted and flipped it to the other side. That's all it is. Now, for us here, again, we're coming back to this first page. This is partially connected with A, okay? If it's a reflection across the x-axis, A is negative. That's it. If the A number, the number where A is negative, if it is negative, then it's a reflection across the x-axis. And we're talking about that A value, that value outside the parentheses. Now, A will have a value. A will have a value. And that's where we start talking about vertical stretch or shrink. But if that A is negative, specifically negative, then it's a reflection across the x-axis. It could be -2. So it will be a reflection across the x-axis, and it will have something else with the 2. The negative is specifically the negative is what a reflection is. All right? Now, if the A value is positive, there is no reflection. It specifically has to be negative for it to be across the x-axis. Well, isn't there more than one axis? The y. For it to be a reflection across the y-axis, the x inside those parentheses, the sign in front of it inside parentheses, has to be negative. Okay? If it's outside the parentheses, it's across the x. Or if there is no parentheses, it's across the x. It doesn't flip at all. So as we've seen already, the graphs we've done up to this point have not had a negative. They just stayed the same. If we put that negative in front of it, let's just go on and do that. So I'm going to have to delete it. That's fine. Negative math. Figure that out. It's not going down. It was going up. It's a reflection across the y-axis. All right. Now for this here, in most of these, a reflection across the y-axis for the absolute value is not going to do a whole lot. And I can say that, but it means more if we can see it, okay? This is going to be real quick, all right? The graphing calculator is going to graph the graph in blue, then it's going to immediately graph the one in red. It's going to do one at a time, all right? So be watching this. So did it one after another. It did it pretty quick, yes? What happened to the blue one? It's covered up, yes? And what it did is it took every point that was to the right of the y-axis and graphed it to the left. And every point that was to the left of the y-axis is now on the right. It just graphed it onto itself. That's why it doesn't do much, because it literally flipped onto itself. The only way we would see something is if we said x plus 1, and then okay. I don't need the parentheses. Because I moved it one to the left and then it flipped it over, so we actually do have it not on itself. Does that make sense? Because it moved one to the left, and then we reflected it across the y-axis, and now it's one to the right. So that's the only time across the y really makes a difference. And it's because they were sitting on the y-axis, so they flipped across the y-axis, and it's the exact same thing. So let's look at this first one here, the graph of p of x equals -x squared. So we're not going to graph it, but its parent function would be what? Quadratic. And the main reason we know is because of the square of the power of 2. So its parent function, we would say, is quadratic. It's our we can do this graphically, we can do this algebraically, because our parent general form, f of x is equal to a x minus h squared plus k. There is no h and k for our p of x. So there is no movement left or right, there's no movement up or down. But the value of a is negative, yes? And since the value of a is negative, specifically negative, this is a reflection across the that's it. Questions on this here? What is the parent function for the next one? Linear. You don't necessarily, especially on the homework, have to write out the parent function, because if it asks for it, or I just want you to list the parent function, and I'll specify, but it's just linear. Fine. Now the general form for linear. A times x minus h plus k. There is no h and k. There's no parentheses. Value inside parentheses are being added to it, so they're both 0. No movement left, right, no movement up or down. But the value of a is negative, so this is a that's it. That's the only transformation. Questions on this here? Now we'll go on and look at these three here. Now this first one, g of x equals x plus 3. What's its parent? Linear, because we just have x, yes? Linear. Okay, we'll say linear. Now I'm going to write the general form. Now I will say this, you do not have to write this every single time. I'm not going to count off if you don't write it every single time. If you have it there and you're referencing back to it, that works just fine. Or if you like having it written there so that you can look directly at it and see what matches up with what, go on and write it. There's nothing wrong with that. But looking at this here, the main difference, or what's changing, is our 3, yes? What does the 3 connect with? A, H, or K? K, it's on the outside, yes? K moves which direction? Up or down, yes? How far are we moving, up or down? 3. Which way are we moving? Up, so it's going up 3. It's linear, and its movement is up 3, because we have plus 3. Yes? Let's look at number 3. H of x equals, parentheses, x minus 2, close parentheses squared. What's its parent? Quadratic. Now, just looking at that, can anybody say what the transformation is? Well, because the general form is a times x minus h squared. So we have left or right, yes? Because h is what this is corresponding to. So that would be a movement of 2, yes? So now we're moving left or right. Since it's inside the parentheses, that h is the opposite of what we think. And since it's minus 2, again, it is very tempting to want to say to the left, but it's actually to the right. Now, I did write the general form above it, because if we look at the general form here, the x and x match up like they've always had. Well, here, the minus and minus match up. So really, it's just telling us h is positive 2. Positive is right. But again, I think it's sometimes a little bit easier just opposite of what we think. If it's negative, it's to the right. If it looks positive, it's to the left. Number 4. I don't know if y'all have already written that one. Its parent function is what? Absolute value. What would be the transformation? So there's no values for H or K, right? There's nothing added outside, there's nothing added to it inside, which means left, right, up, and down is not going anywhere. It's reflection across the X. Since the value, the sign for A is negative, since that is negative, it's a reflection across the X axis. Questions on this here? Now, the next thing we are going to talk about is vertical stretch and shrink. So vertical stretch and shrink means it's going to either increase faster or slower. But I'm going to stop here. So we're going to stop here. We will pick this up tomorrow.